I want to go over one more example of a function that's either even, odd, or neither even nor odd. Then after that, I want to talk about increasing, decreasing, and constant functions. So let's say we have the function f of x equal to the square root of x. Is this function even, odd, or neither? Here I have the graph of the function. Let's verify this a little bit by plotting some points. So the function is f of x is equal to the square root of x. So if I plug in 0 for x, I'm going to get the square root of 0, which is 0. So I'll have the point 0, 0 on the graph. If I plug in 1, I'll get the square root of 1. So I have the point 1, 1. And I can plug in, let's say 4. That's something I know the square root of. The square root of that is 2. So I get the point 4, 2. And I can continue this. I can actually plug in things in between 1 and 4, but I won't get such nice square roots like that. So this looks right. Now, looking at this graph, remember that a function is even if its graph is symmetric with respect to the y-axis. This graph is not symmetric with respect to the y-axis because there's nothing over here. And here's the y-axis, and for it to be symmetric with respect to it, this has to have a mirror image on this side, and we don't have that. So it's not even, and it's also not odd because it's not symmetric with respect to the origin. In other words, what we have here is not pictured down here. So it's not odd, which makes this neither even nor odd. Now let's look at the equation. Remember that we have an even function if for every x in the domain, negative x is also in the domain, and f of negative x is equal to f of x. And we have an odd function if f of negative x is f of x times a negative. There's something interesting about this. Notice that we don't have anything pictured over here because we can't put negatives in the square root. Because we can't put negatives in the square root, we can't even follow this definition, because remember the definition says for every number x in your domain, its negative also has to be in the domain. Well, 1's in the domain, but not negative 1. You can't take the square root of a negative 1. So because you can't put the negatives in the square roots, you can't plug it into the function, so you can't even check these two. So that's why it's not even or odd algebraically, just by looking at the graph. So it's neither even nor odd. Oops, sorry about that. Let me scroll back down. Okay. What does it mean for a function to be increasing, decreasing, or constant on an interval? So I'm going to give you the definition, the mathematical definition for increasing, decreasing, and constant. And then we're going to look at graphs, and we're going to be able to figure out if they're increasing, decreasing, or constant just by looking at the graph, which is going to be a lot easier than working with the definition. I'm going to give you the definition. You're not really going to use it, but I want you to be exposed to it because you're going to see it again in calculus. So here I wrote the majority of the definition. I'm going to fill in some blanks here. So a function f is increasing on some interval I if for any x1 and x2 in that interval where x1 is less than x2, we have f of x1 is less than f of x2. This is the mathematical definition of an increasing function. So let me give you a picture of an increasing function. Say we have f of x is equal to 3x. What would this look like? Well, the y-intercept is 0, 0, and it has a slope of 3. So the graph is going to look something like this. So up 3 over 1. its domain is negative infinity to infinity. So choose any interval you like between negative infinity to infinity. In fact, you could just use that interval, negative infinity to infinity, but you could also use something like 2 to 5 or negative 1 to 7, any interval. And you want to choose two numbers in that interval. So I'm going to go with this interval here. So just looking at my x-axis, let's say I'd go with negative 2 and I go with, let's say, 1. So let x1 be negative 2 and x2 be 1. Well, obviously x1, which is negative 2, that's less than 1. So x1 is less than x2. So I have this property here. I chose two numbers, x1 and x2, that are in my interval negative infinity to infinity. Now I'm going to plug those values, negative 2 and 1, into my function. So if I plug in negative 2 into my function, well, it's 3 times x, so I get negative 6, which is way down here. And if I plug in 1 into my function, I get 3. And you see that negative 6 is less than 3. So f of x1 is less than f of x2. Now here I just chose any two numbers that are in this interval where x1 is less than x2. And what I showed was if I plug them into my function, my numbers, the value of the function at x1 is less than the value of the function at x2. And you can see that. Whatever I plug in here, this number for the y, is going to be less than this number here. But this will work for any two numbers that you choose between negative infinity and infinity. So like if you let x1 be 10, x2 be 500, then f of 10 will be less than f of 500. Visually, how you can tell a function's increasing is you want to pretend like you're a car on your graph. And you're looking from left to right. So you're going, your eye's following this x-axis, and you're seeing what's happening to your function as you go from left to right. So you can see that if we're going this way, my graph is going upward, and that means we're increasing. As long as your graph is constantly going upward, then you're an increasing function. Now let's talk about decreasing functions. So I'm going to erase this, and I'm going to erase this and keep everything else the same. Let's make this black here. So a function f is decreasing on an interval I if for any x1 and x2 in your interval where x1 is less than x2, we have f of x1 is greater than f of x2. Let's look at an example. We could do a line again. Let's say f of x is equal to negative 1/2 x plus 1. Now this goes through 1 here, and the slope is up 1 over 2. So it's going to look something like this. I'm just sketching it. It doesn't have to be perfect. Again, the domain for this function is all real numbers. So I can just choose an x1 and an x2, but I want x1 to be less than x2. So let's say 4 for x1, and let's do 6 for x2. Okay, definitely x1 is less than x2, so I have this property here. Now I want to show you that if I plug in x1 into my function, so f of x1 is f of 4, that will give me negative 1/2 of 4 is negative 2 plus 1, I get negative 1. If I plug in x2 into my function, that's f of 6. Well, 6 divided by 2 is 3, and then I have this negative, so I get negative 2. And notice that -1 is greater than -2, which tells me f of x1, which was equal to -1, is greater than f of x2. So it gives me this inequality that I was looking for. And you can do this for any two numbers you want. As long as x1 is less than x2, for this particular graph, if you plug in that x1, whatever you choose, into f, it's going to be, this number is going to be larger than what you get for f of x2. And a way you can see this with the graph is if you're a car driving along the graph, if you're trying to go from left to right, you'll see that your car is going downward. And when it's going downward, that is a decreasing function. Now let's talk about a constant function. A function f is constant. Let me erase this. I'm going to erase this. I'm going to erase this. So function f is constant on some interval I if for any x1 and x2 such that x1 is less than x2, we have that the values of the function are the same. Here I'll give you an example. Let's just say we have f of x is the number 4. So this is a horizontal line going through 4. And visually you can probably already tell what's going to happen here. From left to right, you're not going up or down. So this is a constant function. But again, you can choose an x1 and an x2. Let's say x1 is 9 and x2 is 30. Well, 9 is less than 30. You can see that this holds. But f of 9, well, the function's 4. So there's no x. That tells me that when I plug in 9, I'm going to get 4. And if I plug in 30, I'm going to get 4. So 4 is equal to 4. So f of x1 is equal to f of x2. You can do this for any of two numbers here. And you can see that the car is just going to go straight. It's not going to go up or down. So that would be a constant function. Now we can have a function that's increasing in some places, decreasing in others, and maybe it's even constant in some places. We're going to see that. So here I'm going to give you a picture of a graph, and I want to determine the intervals for which the graph of the function is increasing, decreasing, and constant. So here I don't even give you an equation. I just say, hey, this is a picture of a function. Let's call this function f. So what I'm going to do is I'm going to write where f is increasing, where f is decreasing, and where f is constant. And of course, it might not be one of these anywhere. First, let's talk about the domain of this function. What is its domain? I'm just going to put D for domain. So the domain is from -6. My x values go all the way to, it looks like this is 7, so 6.5, so 6.5. And the range is how far up and down you go. Looks like the lowest value is -2. And the highest value is 1. Looks like we go to 1.5. Okay. So when we talk about intervals, we're going to look at the x values. Okay? We're going to choose an interval in the domain. So pretend like you're on a car. Let's say you start here, okay? The leftmost portion of your graph. And then you're going to go along this graph from the left to the right. Now, as you go along this graph, notice that I'm going downward, okay? That means I'm decreasing on this piece. Then when I get here, I start going up, so I am increasing. When I get here, I'm decreasing. And then at this point, I turn and go up. And I go up until here. So f is never constant. So now we can just erase this and put never constant. Or f is not constant anywhere on any interval. Maybe we should go with increasing first. So f is increasing on the interval. Now, be careful here. A lot of students make the mistake of looking at the y values. You're always going to look at the x values. So you're going down until we reach here. This corresponds to the number -1. So we're increasing from -1 to, okay, go this way, to the number 2. And then we're also increasing on the interval from 4 to 6.5. Now I want to mention that different textbooks will tell you to use parentheses, and other textbooks will tell you to use brackets. It depends on what textbook you're using. If you're my class, you're going to be using these brackets here. So what this is saying is that for any number between -1 and 2, including -1 and 2, we are increasing. So you choose a number here in between -1 and 2, and one that's less than the other, and if you plug into the function, the f of x1 will be less than f of x2, just like the definition explains. Okay, f is decreasing. Well, it's decreasing from -6 to 1, -1 here, because we stop here at -1, we're increasing, and then we decrease from 2 to 4. Let me write this one a little bit better. It's -1, so it's a little more clear. And now we've found all the places that this function is increasing, decreasing, and constant. Let's try another one. Let's call this function g. So I'm going to put the same thing here. G is increasing on the intervals. G is decreasing on, and G is constant. Okay, imagine you're a little car going for your trip. You'll see that here you're going down from left to right. Remember, we don't start somewhere over here and go backwards. We're going from left to right, and we're going down, 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 always going down until we hit here. Once we get here, we are constant. And then here, we start going up. And then here we go down. I always like to write the domain and the range, just as an extra exercise. The domain is -6 to 8. The range, how far up and down we go, we're going all the way to here, which is -5. Lowest number first, biggest number is 2. Okay, we're increasing on the interval this is decreasing. So increasing is only here. Increasing from 2 to 4. There's nowhere else that we're going up. We're decreasing from -6 to -1. -6 to -1. We're constant from -1 to 2. And then we're increasing from 2 to 4, which we already wrote, and then from 4 to 8, we're decreasing. We're going to move on to local minima and local maxima, which is also called local extrema. Let me give you a few definitions. A function f has a local minimum at x is equal to c if there is an open interval I containing C so that for all x1 in your interval, f of x1 is actually greater than or equal to f of c. I'm going to give you the definition first, and then I want to talk about what it means visually. So I'm going to give you a graph. Let's say the graph looks like this. It's a parabola. We have a minimum. If you can find so visually, you want to think a minimum as a valley. So let's say this is x is equal to 3, okay? This point down here, you can see that this is the lowest point of the graph. It's a minimum. And the f value is the minimum. So we have a local minimum, and let's say this value is -2. So we're going to have a local minimum at x is equal to 3 and a local minimum value of f of 3, which is -2. So the lowest point on my graph is this -2. So what this is saying is that you can find an open interval. So you can find some numbers behind 3 and above 3, so that when you plug them into your function, you're always sitting above this minimum point here. That's the idea. Let me give you another picture. So let's say we have something like this graph here. We have two valleys. You can see I have one here and one here. Let's say this is x is equal to -4, and again, let's say this is x is equal to 3. And I want this to be, let me adjust it a little bit, like that. So wherever the bottom of my valleys are, I have local minimums. So that means I could find a little interval around this number -4 and around this number 3, that anything in that open interval will always be above that value. So just think about valleys of a graph. So here I'm going to have two local minimums. My minimums are x is equal, well, my local minimums at x is equal to -4 and x is equal to 3, but you're going to have a minimum value that corresponds to these two y values. So if this is, let's say this is -5 and this is 1, then you're going to have a local minimum value of 1 and -5. Okay? So the minimum value will be the y, and if I say the local minimum at, you're looking for the x coordinate. Now notice that I also, for this particular graph, I have a hill. What do you think that would be called? That is going to be called a local maximum. So let's erase this and put the word maximum. And I'm going to change just a couple of things. So we're going to have a local maximum at x is equal to c if there's an open interval containing x is equal to c, so that for all x1, so this means in, sorry I didn't write that out, that f of x1 is going to be less than or equal to f of c. So let's say at this number is x is equal to 1, then we would have a local maximum at x is equal to 1. So local maximum at x is equal to 1. And let's say this number, I don't know, let's say 6. And local max value of 6. So overall, you don't really have to memorize these definitions. I just want you to visually understand what a local minimum and a local maximum are. Local minimums are valleys in a graph, and maximums are hills in a graph. So here I have a hill, it's the top of the hill. So we have an x value and a y value. Valley, we have a bottom of a valley, we have an x value and a y value, okay? We're going to look at more examples. So here I'm going to put that down. Hills correspond to maximums. Plural mean more than one maximum is maxima. And valleys correspond to minima. So if we have one minimum, or we're going to have more than one minimum, we might have, like here we had 2, we'll have 2 minima. And you might see this word extrema, which means we either have maxima, minima, or one maximum, one minimum. It's just these special points. Okay, I also want to give you a definition of an absolute maximum and an absolute minimum. So this is going to be similar. You're going to think though as like the tallest point on a graph and the lowest point on a graph. If we look at this picture here, notice that here I have a minimum and here I have a minimum. But this one is the lowest point on the entire graph. This one, although it's a minimum, it's not the lowest point. You can see the y value here is much lower than this one. This would be the minimum, the absolute minimum. And a maximum, the absolute maximum, we don't have one for this graph. We have a local maximum, but you can see that this y value is not the tallest point on this graph. We actually have higher points, so stuff way up here. And you can see that we'll have y values corresponding to x values over here that go way up in the graph. So let me just write the definitions down. So you can always refer to those if you get confused, but visually that's what you want to do. You always want to use the graph to spot out maximas and minimas. So let f be a function defined on some interval so it has some kind of domain. An absolute max is when there's a number u such that, so maybe I should say we have an absolute max, sorry about that. We have an absolute maximum at x is equal to u if for all x in your interval, then f of x is less than or equal to f of u. I'm going to copy this. In fact, I'm going to change this color to green. I'm going to change this inequality to green. I'm going to copy this definition and then give you the definition of an absolute minimum. So we're going to have an absolute minimum. So let's erase this word. Let's make this red. And then we're going to change this sign to greater than or equal to. Okay, so here are the definitions. I just want you to have them. I'm going to explain them visually, and then we're going to look at some examples.